All right, so I will try and get through the rest of the lecture as quick as I can so you guys have enough time to work on your cars or vehicles. I don't want to pin you down to a car for anyone that's not doing a car. So our last chapter is inductance, and so this is we learned about how we create induction, and now we're going to basically talk about inductors. So an inductor is what we can plug into a circuit that will behave with all the properties of what we've been talking about. And in the most simplest terms, an inductor is just a solenoid. So the circuit symbol looks like a solenoid. And so what an inductor is it's used to produce a desired magnetic field at a certain point in a circuit. You can use a solenoid, a toroid, a coil of N turns. So any of those could be an inductor. So an inductor uses symbol L, and the inductance is how we measure sort of the strength of an inductor, sort of like capacitance for a capacitor. And we also use L for inductance. And it has units of henries, which is another new unit. So that's our symbol, and our units are henries. What is a henry? Tesla meters squared per amps. And our inductance is measured by the number of turns in the coil or solenoid or toroid times the flux over the current. And so that's going to change based on whatever is happening in our circuit. So this isn't like you're going to pick up an inductor and it'll have an L value printed on it, because of course this value is going to change as you use your inductor. There's a term that you might see in the book if they say the magnetic flux linkage is this. The magnetic flux linkage is just N times the flux, so that top term. And we've had the permeability constant for, what, a week? Now we get a new unit for it. So the constant itself, 4 pi times 10 to the negative 7th, doesn't change. But now we can put that in terms of henries. So the units on it can be henries per meter. All right, so if you've got a solenoid of cross-sectional area A, and you want to find the inductance per unit length, then the inductance per unit length would be big L over little L being the length. So you just take your inductance equation and put a little l in the denominator, and we can relate that little l to the total number of turns. So last week we said the total number of turns is equal to the number of turns per unit area, or unit length, times the length. So that gets a length in the numerator as well. And then our simplified flux was B times A. So this L and this L will cancel. And now we have a relationship between the turns per unit area and B and A and I. So that's something that might come up, but we're going to use that. So for a solenoid, if we put the B field that we found last week for a solenoid in here, mu naught I times little n, and do a little algebra on it, then we see that this equation becomes mu naught n squared times A. So that would be the inductance per unit length for a solenoid. And then you could do the same thing for a toroid on your own. Since we know the equation for a toroid, you could plug that in as well. So with that information, example 30, 0.3. Let's see. So I basically made that our example. So our example says find the inductance of a toroidal solenoid with cross-sectional area and mean radius r, closely wound with n turns, with a non-magnetic core. A lot of information that we haven't really talked about but isn't really super important. Assume that B is uniform. So the first thing we have to remember is what's the B equation, the magnetic field equation that we derived last week for a toroid? What was it?
B is
mu naught
n
n.
over 2 pi r.
Is that big N or little n?
Big N. So it's the number of turns.
Okay, so you guys are saying that for a toroid, B was mu naught I big N over 2 pi r. So using, well, they're not asking for inductance per unit length. They just said inductance. So if we take our equation for inductance that we have on this slide, which is N times flux over I, so what's the next step that I could do to this equation to incorporate something to do with our B field for a toroid? What's that? Solve this one for I? Sure. What would that be?
2 pi r b.
Okay, yeah, we could plug that in for I. So then we'd have N times the flux times mu naught N over 2 pi r b. Anything else we can do? So I'll go back to this slide for the solenoid. What did we do with the solenoid to get a simplified equation?
Sub for flux.
Sub for flux. Okay, so the simplification would just be B times A for the flux. And then everything else we had. So the B's cancel, which is cool. What would the area be? What would the cross-sectional area be for a toroid? What would the cross-sectional area be for the toroid? Would it be... Okay, that's what I was wondering. Okay, so I had to look at their picture because I wasn't sure. So the 2 pi r, I'm going to go with the way the book drew this. They drew the toroid as sort of a cylindrical shape. So the cross-section of it would look like a square. Is that looking three-dimensional to anybody?
Yeah.
Sort of. Okay, so this is the cross-sectional area A. And then the R is found from the center up to this. So this 2 pi r would not be associated with this area at all. And so I don't know that we can actually reduce that any further down. So what we have now is mu naught n squared times A over 2 pi r. And that's what the book got. So I guess that's as far as we can take it. Okay, so that's kind of a weird problem. Okay, so moving on, now we've got some equations for different kinds of inductors. Now comes a really weird concept. Mutual inductance. Let's say you've got two coils very close to each other, like this. They could even be inside each other, doesn't matter. But they're not part of the same circuit. If you change the current in one of them, so for this picture they're changing the current in the big coil, and they call that I1, it's going to produce a changing magnetic field and thus a changing magnetic flux through the other one. So if your current is increasing in the big loop, then the B field that creates is going to be increasing through the other loop. So the other loop is going to say, whoa, 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 I don't like the B field, this external B field changing. I'm going to create an induced B field to oppose it, going in the opposite direction. And the induced B field is going to create an induced current that would be, what would it be? It would be in the opposite direction of that I1 current. So you get an induced current in this other coil because there's a changing current in the first coil. And so that's the basis of a transistor, a transformer, where you've got one coil attached to a circuit where you can change the current in it, another coil completely disconnected from that circuit, disconnected from any power supply, but it's close enough to feel the changing B field, and that will induce a current in the second coil. So you also, of course, get an induced EMF in the second coil. And then this is where it gets weird. The induced EMF in the second coil will induce an EMF in the first coil. And they call that first one self-induced EMF, since it was the one that had the changing current. And so it, just because it has that nearby coil, it gets a now induced EMF onto it. That's weird.
So it feels more of a load because the coil next to it becomes another load that it's driving. So that's why it's, when it's inducing the EMF back towards it, it's feeling the force of driving whatever's on that circuit.
Mm-hmm.
I think it's, is that?
Well, that makes total sense to me. The next slide makes no sense to me. So it turns out that the second coil doesn't actually have to be there for the first coil to get a self-induced EMF. So I agree with Jordan's logic 100%. It makes sense that you have to have the other coil there, that it's having to do work in that other coil that's creating an induced EMF in the first coil, because it's sort of like pushing something up a hill. It's you're applying work, so.
It's like how people steal power, you know, the line next to a power line and get power off that, but the power company can see it.
Right, they can see the load.
Yeah.
Mm-hmm. Yeah, but this is the part that I don't really understand. Self-induced EMF. So if you vary a current in your circuit with a coil of wire in that circuit, it will induce an EMF in that same circuit that they call self-induced EMF. So it made more sense to me when you had the second coil nearby, and I don't really get this, I'll just be full honesty, I just don't get it, that you get self-induced EMF without the other coil nearby. But apparently it happens.
Maybe it's because an inductor is a storage element, and so it's storing the different kind of current and also the different voltage, and so that different voltage would cause a self-induced. You know, I don't know, I'm just thinking. I know it's a storage element from what I've been told,
Okay, so I mean maybe that's the way that we can sort of jive this, is if we treat it like a storage element, the way that we treat a capacitor.
Like over time it is actually two different coils, and so that's what's causing the EMF.
Whoa.
Or you can have an inductor in a
Trippy.
circuit, so it only really becomes a transformer once there are two.
Right.
So it's still storing a current, it still has a voltage, it still loads. And so when we're analyzing it in circuits, we're treating it not like a capacitor because they're different elements, but it's that same sort of, it has the real part and it has the storage part. So it has the behavior that it would
if we were just looking at the impedance, and then it has the behavior that the circuit would have storing your unit in the inductor. So maybe it's a self-induced, that's why it's called self-induced, is because you only need one. But for the change, which it sounds like that's what they were saying with 2 coils, would be a transformer.
Uh-huh.
So that would be, the difference is you're stepping down or stepping up output voltage, and that's what the change is. So it's basically acting back on it.
Well, yeah, I mean, that part I understand, but when you don't have something else there to act back on it, it's surprising, I'll just say. It's surprising that you still get the self-induced EMF. But if, you know, the way you guys have described it as a storage element, it makes sense, like, that it's capable of doing this work on another coil. The other coil doesn't have to be there for it to still be capable of providing that work. So maybe that's the way we just have to think about it. All right, so let's talk about this self-induced EMF. Self-induced EMF has our EMF symbol with an L subscript, so we know it's associated with our inductor. Okay, so we've got and again, that negative in the equation isn't necessarily indicative of the direction of the induced EMF. We still have to use our logic to figure out the direction of the induced EMF. It's just reminding us that the induced EMF is opposing a change in the current. That's why it's derived. It's from Faraday's law. It's opposing the change in the current. So this is creating a B field, but it's only going to create a B field when the current changes through the coils. So our induced EMF is not constant. It's dependent on the change in the current. So if your current's constant, there's no induced EMF. So we can draw the direction of the induced EMF, and this is what we figure out logically. So if you just turn on the current in a circuit that's got an inductor in it, suddenly you've got current flowing through the wire. So you go from 0 current to an increasing current. Your inductor is going to do all that it can to block that current. So at time equals 0, the induced EMF is upward. The arrow is indicating that it's opposite. It's opposing the current, incoming current. And at exactly time equals 0, it will block current completely. So no current will go through that inductor at time equals 0. If the current's been on for a while and the inductor has gotten used to it, and then suddenly you try turning the current off, and now you've got current decreasing in your wire, you're going to create an induced EMF to try and boost the current back to the level it was. So now you're going to have a downward induced EMF in the direction of current, trying to continue driving the current through the loop. So there's nothing really for me to write on the board here. So let's see, example 30.4. I don't think there's really complicated algebra here, but this is something we can talk about. So it says, if the current in the toroidal solenoid from our previous problem increases uniformly from 0 to 6 amps in 3 microseconds, find the magnitude and direction of the self-induced EMF. So you have to look at the picture in the previous example in order to answer the direction question. So for the induced EMF, we can figure that out fairly easily. They solved for the L term that shows up here. If you look in the evaluate section of example 30.3, they plugged in numbers and gave a value for L of 40 times 10 to the negative 6 henries. So that would go in for L. And then if we treat this like an average EMF, then you could call this delta I over delta T and make that I final minus I initial over the change in time. Then you can plug in the currents that they have. So the calculation itself isn't overly complicated, but my question to you, based on the drawing that you see in example 30.3, can you figure out what the direction of the induced EMF is based on how they've wrapped the current around that toroid? Okay, so I've attempted to recreate that picture. And current's increasing or decreasing in this problem? It's increasing. And so we learned from this picture, the induced EMF is going to be opposite to that. So I don't know how that really works with this toroid. I'm guessing that the induced EMF is in the opposite direction, but let's see what they say. According to Lenz's law, the direction of EMF is opposite to that of the current. This corresponds to the situation in figure 30.6c, which I don't have in front of me. The EMF is in the direction from B to A. Okay, well, based on their drawing in 30.5, that's not really going to help me. So, all right, we'll just go with it that it opposes the direction of the current. That's a very weird picture to base it off of.
Can we use the right-hand rule then for that, like they're modified? That if the current is traveling around the...
Oh, you could figure out the direction of the induced B field, but as far as the answer of which direction the induced EMF goes in, it's either in the direction or away from the direction of the current.
Right.
And so we wouldn't need to use our right-hand rule to answer that. But if we did want to find the direction of the induced B field, what would it be? Yeah, you use your modified right-hand rule to figure that out. So in this case, your fingers curl in the direction of the current. Your thumb would show the direction of the B field. Yeah. So if our current is increasing in the loop, what's the direction of our induced current? So I know it's hard to see this. My increasing current is sort of like into the middle of the toroid. All those wraps, the currents would be going towards the middle. So the induced current, to oppose the increase, would be flowing towards the outside of the toroid. And so that shows me that my thumb is to the left, making my, so this would be the direction of my induced current, and also my induced EMF direction, and then that would create an induced B field that was this direction. Any questions so far? People following along for the most part? Okay. All right. So we're creating this magnetic field by putting a changing current through an inductor. So we learned with charged particles or capacitors that we can store energy in the form of a potential difference. And so we can do the same thing with a magnetic field. And in this case, instead of having a potential difference the way we did with capacitor plates, we're storing energy in the form of this B field. So the stored energy from an inductor, the equation for it is 1/2 Li squared, which I'm not remembering. Does anyone remember? That seems like it's really close to what it was for the electric field in a capacitor. Did it have a similar form to that?
Probably.
Like 1/2 CV squared, or?
Yes.
1/2 CV squared. Okay, I feel like the form of it was very familiar to me. So this is stored energy in a B field. Yeah, okay. Okay, so the whole point of this is to kind of build up this idea that inductors are very similar to capacitors. They store energy in the form of a magnetic field, and then you can get that energy out at a desired point in time. And how we did that with capacitors was the RC circuit, and how we do that with inductors is the RL circuit. And the behavior is very, very similar. So our equations we had for the RC circuit looked like this. We had whatever the maximum value was outside the parentheses, and then 1 minus e to the stuff or e to the stuff. And so if it was just e to the stuff, that was exponential decay. And if it was 1 minus e to the stuff, that was exponentially approaching an asymptote. And this would be your asymptote that it's approaching. So I'm just reminding you this because your RL equations are going to look very, very similar. Are we ready to dive into this, or do people need I guess we've only been talking for half an hour. Okay, you guys ready? Got our hands on our undies so we don't get blown away. Okay, RL circuit. We've got two cases, rising current and falling current. We've got this switch here where it can go from A to B. So the first thing we do is we move the switch to A, and that starts current flowing clockwise around our loop. So this is really the important part of our loop. And what we're looking at is how the current is interacting with our inductor. So as soon as the switch closes, it starts flowing current across the inductor. The inductor hates that. It drives an induced EMF in the opposite direction. So at time equals 0, no current passes through that inductor. So the equation that we get for current through the inductor has this form, EMF over resistance. That's like V equals IR, except I equals V over R. And then 1 minus e to the stuff. So we learned 1 minus e to the stuff is the one that starts at 0 and rises towards an asymptote. And that makes total sense because our current starts at 0, and then as the current's been going for a while, the inductor kind of relaxes and says, okay, I guess you can pass current through me. And as the current is not changing as rapidly, the inductor says, okay, I'll back down, I'll back down. And the induced EMF gets smaller and smaller and smaller until the current is now steady state and we no longer have any induced EMF. So the current and the induced EMF are going to be sort of in opposition to each other.
It's kind of like a flywheel, really, related mechanically. I mean, the inertia of the flywheel resists movement, and then once you get it moving, it spins at its speed, and then you stop applying force, and it continues spinning.
And then it's going to reduce or
dissipates its energy.
Mm-hmm. So probably has this very similar curve of like needing to get itself up to momentum. Once it's got the momentum, it's like self-momentum.
Yep.
If you stop driving it, it'll keep turning and have a decay curve, probably very similarly. Yeah, okay. So these are important. This is an important equation to have on the board and in your notes. But what was useful last time was to kind of think about the extreme cases. The time equals 0 and time equals infinity for what's happening for anything. So our rising current case. So the current across the inductor, it's going to approach our asymptote. The max value that the current will be is the EMF of the battery divided by the resistance. So you'll notice that in our exponent, we've got a new variable, tau sub L. So before with the RC circuits, we had the capacitive time constant. Now tau sub L is called the inductive time constant. And it's, what is it, L over R. All right. So that's our induced current, or the current across the inductor, through the inductor. This isn't the induced current. This would be the current being driven by the battery. And so across the inductor, it's not allowing any of that current through, which would be different than the induced current.